March 6, 1944, high above Berlin at 28,000 feet, the 56th Fighter Group found themselves locked in combat with German fighters in what would become the largest aerial battle scene over Europe up to that point. Amid the chaos, American Thunderbolt pilots noticed something that left their Luftwaffe opponents stunned. German aircraft, following their standard evasive routine, would pull into steep climbs to shake off pursuers. For the previous year, this tactic had worked nearly every time. The hefty P-47 Thunderbolt simply couldn't keep up with a climbing Focke-Wulf 190 or Messerschmitt 109. But on this day in March, everything changed. The Thunderbolts remained glued to the German fighters' tails, even through climbs that should have been impossible. At nearly 28,000 feet, both American and German planes hovered near stall speed. Then, the Thunderbolt struck. Smoke blackened the sky as German aircraft were hit, and pilots leaped from their doomed planes. By the end of the mission, the 56th Fighter Group claimed 11 German planes destroyed without losing a single P-47. The transformation had arrived. A modification to the Thunderbolt's propeller had erased its most glaring weakness, reshaping the tactical landscape over Europe. The story of this breakthrough begins in the engineering departments of two American propeller manufacturers during the harsh winter of 1943. While Allied bombers suffered over Germany and fighter pilots filed reports describing enemy planes escaping through climbs, engineers raced to solve what seemed like a deceptively simple problem. The Pratt & Whitney R2800 engine generated a staggering 2,000 horsepower, yet the P-47 Thunderbolt climbed poorly. Early production models were equipped with narrow-blade, Curtiss, electric propellers, which couldn't convert that raw power into vertical lift. These blades were designed for speed, optimized to slice through the air with minimal drag above 350 miles per hour, at lower speeds during climbs. Even with the engine at full power, the narrow blades couldn't grab enough air to generate thrust effectively. Engines roared at maximum RPM, consuming fuel and producing heat, but the aircraft struggled to ascend. January 1943, Republic Aviation Corporation, Farmingdale, Long Island. Alexander Cartelli pored over combat reports from England with mounting concern. German fighters would dive into bomber formations, attack, then pull into steep climbs that the Thunderbolts simply couldn't follow. Performance charts confirmed the problem. Early P-47 models took far too long to reach combat altitude, while Focke-Wulf 190 AS and Messerschmitt 109 gigaseconds could climb much faster. This performance gap cost lives. Pilots were dying in situations where superior climb rates might have saved them. Some commanders in the Army Air Forces even questioned whether the P-47 should continue frontline service. Cartelli understood the engineering issue. Propeller efficiency depends on matching the blade's area to its operating environment. Narrow blades excelled at high-speed flight, where thin profiles minimized drag, but during low-speed climbs, blades required more surface area to convert the engine's power into usable thrust. Increasing blade area seemed straightforward, but the execution was anything but. Changing propeller design affected the entire aircraft system. Poorly shaped blades could create vibrations capable of tearing engines from their mounts. Bad weight distribution could induce harmonics that might rip the plane apart, and incorrect torque characteristics could make takeoff uncontrollable. Republic Aviation needed propellers that offered dramatically more blade area yet integrated into existing aircraft without major redesigns. Two companies set out to solve this challenge: Curtiss-Wright, maker of the original narrow-blade propeller, and Hamilton Standard, a producer of military propellers across various aircraft. Both understood that the winning design would be mass-produced. Tens of thousands of units and would directly impact the survival of thousands of American pilots throughout the winter of 1943. Engineers at both companies tested blade shapes in wind tunnels, calculated stress loads, and built prototype hubs and pitch control mechanisms. American pilots were dying while engineers fine-tuned blade chord lengths and twist angles. Hamilton Standard proposed a radical departure from conventional designs. Instead of thin knife-like blades, they created wide paddle-shaped blades that gripped the air like oars pushing through water. The blades were nearly rectangular for most of their length, before tapering at the tips. Two traditional aerodynamics engineers, the design looked crude, but wind tunnel tests showed dramatic results. It generated far more thrust at low speeds, while sacrificing very little top-end performance. Curtiss-Wright responded with their own wide-blade solution, keeping a more traditional elliptical shape but increasing the overall blade area substantially. Their design featured blade cuffs at the root, which smoothed airflow into the hub and reduced vibration. Both designs represented a massive improvement over the original narrow blades. By April 1943, Republic Aviation had received prototype propellers from both companies. Testing began immediately at Republic's facilities and at Wright Field in Ohio. Test pilots evaluated each design systematically. Results were clear. Both the Hamilton Standard and Curtiss-Wright propellers dramatically improved climb rates. The Hamilton design offered slightly smoother operation thanks to hydraulic pitch control, while the Curtiss design was easier to retrofit into existing P-47s. Neither design dominated in all aspects. The Army made a pragmatic choice, approved both for production. Hamilton Standard propellers would be installed on new P-47s built at Farmingdale, starting with the P-47D-22 model. Curtiss paddleblade propellers would be produced at the Evansville, Indiana factory and supplied as retrofit kits for earlier aircraft in England. This approach prioritized rapid deployment, ensuring American pilots received the performance edge as quickly as possible, rather than waiting for a theoretical best design to emerge. The dual-source strategy also added a layer of complexity for German intelligence. Production of the new propellers began in June 1943, but delays in manufacturing and testing meant that the first operational aircraft didn't arrive in England until late December 1943. Throughout that month, P-47s were flown to RAF Water, where mechanics retrofitted them with the new paddleblade propellers. By early January 1944, the 56th Fighter Group, operating out of Boxted in Essex, had completed the transition. Group Commander Lieutenant Colonel Hubert Zemp immediately grasped the tactical potential. The dramatically improved climb performance allowed his pilots to engage German fighters with vertical tactics that had previously been suicidal using the narrow blade propellers. Zemp organized intensive training throughout January 1944, developing combat procedures specifically tailored to the Thunderbolt's new capabilities. He taught pilots to engage German aircraft in climbing spirals maneuvers that, before, would have left them dangerously exposed. Techniques were refined so that pursuing P-47s could pull sharply upward if enemy fighters attempted to climb away, convert that speed into altitude, and then dive back onto their targets with accumulated energy. What had once been slow, vulnerable climbs became lethal offensive maneuvers. January 4, 1944. Marked a milestone. The entire 56th Fighter Group flew its first mission with all aircraft equipped with paddleblade propellers. Pilots immediately noticed the difference. The Thunderbolts climbed with an eagerness previously thought impossible for a 17 fighter. Vertical maneuvers now retained far more energy, allowing American pilots to follow German fighters into climbs without losing position. The real test came over Germany. During escort missions in late January and early February 1944, American pilots encountered German fighters executing their usual escape tactics, only to find pursuing Thunderbolts matching them in vertical combat. Initially, Luftwaffe pilots assumed they were facing an entirely new type of American fighter. When intelligence officers reviewed gun camera footage showing standard P-47s performing these climbs, confusion rippled through German units. How could the same aircraft they had evaded for months now match their performance in the vertical? March 6, 1944, provided dramatic confirmation. Lieutenant Colonel Zemk led 48 Thunderbolts on a bomber escort mission to Brunswick, routing over Berlin. Luftwaffe controllers scrambled more than 80 Messerschmitt 109s and Focke-Wulf 190s to intercept the incoming bombers. As the formation approached at 24,000 feet, German fighters attacked, diving through bomber formations before pulling into steep climbs to escape the escorts. For the first time, Thunderbolt pilots matched German aircraft in vertical engagements. Captain Robert Johnson, Lieutenant Walker Mahurin, and other 56th Fighter Group pilots destroyed enemy planes at high altitude. By mission's end, the group claimed 11 victories without losing a single Thunderbolt. Notably, not a single bomber under their protection was shot down. Returning German pilots reported the troubling reality: American Thunderbolts were now climbing alongside them. Multiple pilots insisted they must have encountered a new type of fighter. but gun camera footage confirmed the truth. These were standard P-47s, performing beyond their previously known limits. LUFT-WAFFE, technical intelligence, scrambled to understand the change. Initial clues came from wreckage analysis in early February, when a shot-down P-47D-23 was sent to the Luftwaffe testing facility at Reck. Engineers immediately noticed the unusually wide propeller blades. However, initial reports underestimated the significance, concluding that the modification primarily improved takeoff performance rather than combat capability. This misjudgment cost the Germans valuable time. Through February 1944, more P-47 groups transitioned to paddle-blade propellers. The 4th Fighter Group received theirs in early February, followed by the 78th Fighter Group by month's end. 6 of 8 Thunderbolt groups in England were flying paddle-blade-equipped aircraft, each immediately noticing enhanced combat effectiveness. German pilots found that standard escape tactics no longer worked, and Luftwaffe losses began to mount. On February 21, 1944, Jagdgeschwader 26 lost 7 Focke-Wulf 190s. In a single engagement with the 56th Fighter Group, unit commander Major Klaus Metasch filed a report detailing his frustration. His pilots had followed established doctrine, attempting climbing escapes when pressed only to be shot down. Metasch demanded clarification. Had the Americans introduced a new fighter type, and did existing tactics remain valid? Luftwaffe intelligence had no clear answer. By March 1944, German engineers realized that American modifications had focused on the P-47's propeller, increasing thrust at low speeds, particularly during climbs. Warnings circulated. American fighters could now contest vertical engagements. Recommendations suggested engaging only when holding a clear energy advantage, disengaging via level high-speed flight rather than climbing away. Yet implementing such changes across hundreds of squadrons proved impossible. Pilots conditioned to climb to survive could not instantly unlearn years of instinct. The transformation became undeniable during Big Week, the massive bombing campaign against German aircraft production in late February 1944. Between February 20th and 25th, the 8th Air Force launched over 3,800 bomber sorties, escorted by more than 3,600 fighter sorties. Most American fighters were now paddle-blade P-47s. The Luftwaffe responded with over 2,000 sorties, but lost approximately 355 aircraft, with another 100 damaged beyond repair. American fighter losses totaled only 28. The combat exchange ratio had shifted dramatically. Pilots discovered that the paddle-blade propellers offered more than just improved climbs. Greater low-speed, thrust-enhanced acceleration out of dives, allowing Thunderbolts to regain energy rapidly after high-speed attacks. This enabled repeated divan climb assaults, keeping the initiative throughout prolonged engagements. Enhanced thrust also improved turning performance at lower speeds. While Thunderbolts still could not outturn Messerschmitt 109s or Focke-Wulf 190s in flat horizontal turns, they could maintain energy in climbing turns, preventing German aircraft from gaining an angular advantage. Major Francis Gabreski, commanding the 61st Fighter Squadron within the 56th Fighter Group, became the leading proponent of the climbing spiral. Gabreski would engage German fighters at altitude, typically around 24,000 feet. Rather than attempting to outturn the enemy horizontally, he maintained speed while pulling into a climbing turn. German pilots, expecting the Thunderbolt to lose energy, followed only to find themselves trapped. P-47s maintained climb rate through 2 or 3 full spirals, draining the enemy's energy until the German fighter stalled or broke off. At that point, Gabreski would reverse, dive on the target, and open fire from an almost inescapable position. Gabreski ultimately claimed 28 aerial victories flying P-47 Thunderbolts, the leading American ace in Europe to achieve all his kills in a single aircraft type. Nearly all of these victories came after his squadron transitioned to paddle-blade propellers. In post-war interviews, Francis Gabreski consistently credited the new paddle-blade propeller as the single most important factor in the P-47's transformation. The modification required minimal adjustments to pilot training. Aircraft now performed exactly as pilots demanded, maintaining energy in situations where rubber-blade Thunderbolts would have faltered. The paddle-blade program was a showcase of American industrial efficiency. From concept to widespread deployment took just 9 months. 2 companies designed, tested, and began manufacturing 2 different propeller types. Republic Aviation retooled production lines at 2 factories, while the Army Air Forces established new maintenance procedures, trained mechanics, and shipped thousands of propellers across the Atlantic. No single innovation was revolutionary. The achievement lay in the speed and scale of implementation. The United States identified a critical weakness and corrected it faster than Germany could respond. German designers certainly had the technical knowledge to make similar improvements. Both Messerschmitt and Focke-Wulf employed experienced propeller engineers who understood the benefits of increased blade area. However, by 1944, Germany's war economy could not support rapid modification programs. Aircraft production ran at maximum capacity, focused on replacing losses with existing designs. Introducing new propeller types would have required retooling factories, recertifying aircraft, updating manuals, and retraining mechanics, efforts that would have cost thousands of fighters when every plane was desperately needed. German engineers were trapped by circumstance. They needed the improvement but could not afford the disruption. This contrast highlights fundamental differences in American and German aircraft development philosophies. American designers prioritized solutions that could be implemented quickly. The paddle blade propeller was heavier and generated more drag at high speeds than narrow blades, but it solved the immediate problem without years of optimization. German designers often sought theoretical perfection, pursuing advanced variable pitch systems that promised superior performance on paper, but few ever reached operational service in meaningful numbers. By March 1944, the paddle blade Thunderbolt had become the standard American escort fighter in Europe, no longer a compromised aircraft awaiting replacement by the longer-ranged P-51 Mustang. The P-47 had evolved into a formidable air superiority fighter, capable of dominating German opponents in most combat situations. The psychological impact was profound. Bomber crews who had watched helplessly in 1943 as German fighters climbed away now saw enemy aircraft intercepted and destroyed in climbing combat. Already demoralized by the increasing numerical advantage of American forces, German pilots faced a new tactical reality. Their previous strengths were neutralized. The Focke-Wulf 190, once superior to the Thunderbolt in nearly every performance category, found itself matched or exceeded in its one remaining area of advantage. The Messerschmitt 109 could no longer rely on vertical maneuvers to escape. German fighter losses rose steadily through spring 1944, and many veteran pilots were downed by Thunderbolts they had previously thought easy to evade. The full impact became clear during the preparations for In May 1944, American fighters carried out intensive operations aimed at securing air superiority over France. Thunderbolts swept across northern France, striking German airfields, destroying aircraft on the ground, and engaging any Luftwaffe fighters attempting to intervene. Paddle-blade-equipped P-47s proved especially effective in these sweeps. When German aircraft scrambled to intercept, they typically climbed from lower altitudes to reach American fighters operating at 20,000 to 25,000 feet. Thunderbolts could dive on these climbing opponents, attack, and climb away before retaliation was possible. On June 6, 1944, as Allied forces stormed the beaches of Normandy, Thunderbolts provided constant air cover. German fighters attempting to strike the invasion fleet or support ground forces were consistently intercepted and destroyed by paddle-blade P-47s. During the first critical 24 hours, the Luftwaffe managed fewer than 100 sorties over the beaches, while American fighters flew more than 8,700. This overwhelming superiority was made possible because American aircraft achieved kill ratios of 4-to-1 or better. By eliminating the Thunderbolt's primary weakness, the paddle-blade propeller directly contributed to the air dominance that made the invasion. Successful DOT statistics confirmed what pilots experienced firsthand. In the first quarter of 1944, before widespread adoption of paddle-blade propellers, American fighters in Europe had an overall kill ratio of roughly 1.8-to-1 against German aircraft. By the second quarter, with most fighters equipped with paddle blades, the ratio rose to 3.2-to-1. By the third quarter, it reached 4.6-to-1. While these improvements were also aided by growing American numerical superiority, improved pilot training, and the inexperience of replacement German pilots, combat reports clearly show that the enhanced climb performance played a decisive role. The most widely used variant, The Curtiss Electric C542S paddle blade propeller featured for blades with a diameter of 13 feet, transforming the P-47 into a more capable, versatile, and deadly fighter. Each paddle blade propeller featured significantly increased surface area compared to the older narrow blade designs. This larger area translated into dramatically improved thrust at low airspeeds. Later production P-47s fitted with the Hamilton standard hydraulic paddle blade offered similar performance, with added operational benefits. Its hydraulic pitch control system was simpler and more reliable than the Curtiss Electric system. Overall blade area was nearly identical between the two designs, and in combat, their performance was virtually indistinguishable. The manufacturing effort required to equip the entire P-47 fleet demonstrated the scale of American industrial capacity. Between June 1943 and December 1944, both Curtiss-Wright and Hamilton Standard produced thousands of complete propeller assemblies. Each included 4 blades, a hub assembly, pitch control mechanism, and mounting hardware. The blades were forged from aluminum alloy, machined to precise airfoil shapes, and heat-treated for maximum strength. Each blade alone required roughly 14 hours of machining, not counting raw material preparation and finishing. Logistics for distributing these propellers to operational units in England were challenging. Each assembly weighed about 650 pounds and required careful handling to prevent damage during shipping. Propellers were packed in wooden crates with protective bracing and transported across the Atlantic on cargo vessels, a journey that typically took 2 weeks. Upon arrival, they were sent to air depot facilities where mechanics installed them on aircraft, a process taking roughly 16 hours per plane. This included removing old propellers, fitting the new assembly, rigging pitch control systems, and performing ground tests. Between January and June 1944, depot mechanics retrofitted over 1,000 Thunderbolts while keeping frontline units operational. Tactical evolution continued through summer and fall 1944 as pilots refined techniques to exploit the enhanced climb performance. One particularly effective tactic was the vertical scissors. 2 Thunderbolts would engage a German fighter in a climbing dogfight. As the enemy climbed to escape one P-47, the second would position itself to strike once the German aircraft lost energy and could no longer sustain the climb. The German pilot faced a no-in choice: continue climbing until stalling, leaving themselves vulnerable to the trailing P-47, or level off to preserve airspeed, allowing the lead Thunderbolt to dive and attack. Another development was the use of paddle blade Thunderbolts in low-altitude ground attack missions. Improved thrust at low speeds enabled heavily loaded P-47s to maintain speed and maneuverability, even when carrying 2,500 pounds of bombs or rockets. Pilots could dive from lower altitudes, reducing exposure to anti-aircraft fire, and then climb away from the target zone more quickly, minimizing vulnerability. Between April and September 1944, Thunderbolts flew over 88,000 ground attack sorties, losing roughly 8 to 20 aircraft to all causes, a loss rate under 1%. The versatility of paddle-blade Thunderbolts ensured their continued frontline relevance, even as longer-range P-51 Mustangs entered service. Many fighter groups chose to retain the Thunderbolt, recognizing that its rugged construction, 8-gun armament, and enhanced climbing performance made it exceptionally effective across multiple roles. The 56th Fighter Group, under Colonel Hubert Zemp and later Colonel David Schilling, flew Thunderbolts exclusively for the duration of the war. Despite opportunities to transition to Mustangs, their pilots trusted the paddle-bladed P-47 as the superior choice for their missions. German fighter pilots who survived the war consistently acknowledged the paddle-blade Thunderbolt as one of the most formidable American aircraft they encountered. Major Gunther Raoul, credited with 275 victories, noted in post-war interviews that the improved Thunderbolts were far more dangerous than earlier versions. He stated that German pilots had to treat the paddle-blade-equipped P-47 with the same respect as a P-51 Mustang, recognizing that the American fighter could match German performance in nearly all combat situations. Lessons from the paddle-blade program influenced American aircraft development for the remainder of the war. The rapid design and deployment showed that incremental improvements to existing aircraft could provide greater operational value than creating entirely new types. The P-47 itself benefited from further upgrades beyond propeller modification. Water methanol injection systems increased engine power to 2,535 horsepower for short periods, and when combined with paddle blade propellers, thrust and performance improved even further. The P-47M, introduced in late 1944, incorporated both modifications, achieving climb rates equal to or exceeding those of any German fighter. The financial investment required to develop and deploy paddle blade propellers was modest compared to the operational advantages gained. Development costs for both Curtiss and Hamilton's standard, including wind tunnel testing, prototype construction, and flight trials, totaled approximately $3 million. By contrast, developing a new fighter aircraft would have cost at least $100 million and required 2 to 3 years before entering service. The paddle blade propeller was a prime example of cost-effective innovation that made American air power difficult to challenge. The program also highlighted the importance of feedback loops between combat operations and aircraft development. Narrow blade performance issues were identified by frontline pilots in after-action reports, describing German fighters escaping via climbing maneuvers. These reports quickly reached engineers, who diagnosed root causes and developed solutions within months. While German forces had similar theoretical feedback systems, their process was increasingly disrupted by the chaos of Germany's deteriorating strategic situation, slowing their ability to implement effective solutions. The strategic impact of paddle blade Thunderbolts extended far beyond direct air combat. By contributing significantly to Allied air superiority over Europe, they allowed ground forces to advance with minimal interference from the Luftwaffe. During the Normandy breakout in August 1944, American troops moved under the protective umbrella of air dominance, maintained largely by Thunderbolts. German ground units attempting to retreat or reposition were constantly attacked by Allied fighters. Improved climb performance ensured that German fighters trying to disrupt ground attack missions could be rapidly intercepted and destroyed by escorting P-47s. The last major large-scale combat involving paddle blade Thunderbolts occurred during the Battle of the Bulge in December 1944 and January 1945, when the German offensive in the Ardennes began. Poor weather initially grounded Allied air operations. Once skies cleared on December 23, Allied air forces launched massive attacks against German troops and supply lines. Paddle blade-equipped Thunderbolts flew hundreds of sorties daily, striking armor, trucks, and artillery positions. German fighters attempted to intervene, but escorting P-47s consistently drove them off. By February 1945, organized Luftwaffe resistance over Western Europe had effectively ceased. German units were being redeployed to defend the homeland against the intensifying Allied strategic bombing campaign. Thunderbolts played a vital role in achieving this air superiority, even if their contribution was often overshadowed by the more celebrated P-51 Mustang. Military historians sometimes downplay the P-47, pointing out that Mustangs scored more aerial victories and penetrated deeper into Germany. However, this perspective overlooks a crucial fact. The Thunderbolt's transformation via paddle blade propeller modification occurred at a moment when German fighter forces still posed a formidable threat. Between January and December 1944, Thunderbolts were credited with destroying 3,382 German aircraft in aerial combat while losing 824 P-47s to all causes in the European theater. An overall kill ratio of 3.7 to 1, comparable to or better than other American fighters during the same period. More importantly, the conversion from a mediocre climber to a capable vertical fighter happened precisely when this capability was most urgently needed. The post-war fate of paddle blade Thunderbolts highlights how quickly wartime innovations can fade from memory. As jet aircraft entered service, propeller-driven P-47s quickly became obsolete. Most surviving planes were scrapped or sold to foreign air forces. The technical achievements that made paddle blade Thunderbolts effective were overshadowed by the revolutionary capabilities of jets. Few of the pilots who had flown these improved fighters were in positions to ensure that the modification received proper historical recognition. Yet the paddle blade propeller represents a fundamentally important form of military innovation. It was not a revolutionary breakthrough that changed the nature of air combat overnight. Rather, it was an evolutionary improvement that took an existing aircraft and eliminated its single most critical weakness through relatively simple engineering. Innovations like this, less glamorous than entirely new technologies, but often more immediately impactful, characterized much of American military success in World War II. The ability to identify problems, develop practical solutions, implement them quickly, and deploy them at scale gave American forces decisive advantages. The engineering principles behind the paddle-blade propeller remain relevant today. The insight that blade area must be optimized for intended operating conditions, rather than maximum theoretical efficiency, applies to modern turbine blade design, helicopter rotors, and unmanned aerial vehicle propulsion. Military engineers still face the challenge of balancing multiple performance requirements across different flight regimes. The German experience with paddle-blade Thunderbolts provides a sobering lesson about industrial and strategic constraints. German engineers understood propeller theory as well as their American counterparts, and German factories were capable of producing similar improvements of resources, and opportunity had existed. But by 1944, Germany's deteriorating strategic position, resource shortages, and disrupted industrial base made rapid innovation impossible. Paddle-blade Thunderbolts succeeded not because American engineers were inherently superior, but because American industry could support rapid development and deployment, while German industry could not. Wars are rarely won by single weapons, brilliant strategies, or revolutionary technologies alone. They are won through the cumulative weight of thousands of incremental improvements, each solving a specific problem, implemented efficiently, and contributing to overall superiority. The paddle-blade propeller was one such improvement, arriving at a critical moment when German forces were still capable of contesting Allied air power. By eliminating the Thunderbolt's primary weakness, it helped establish the air dominance that made the invasion of Europe possible and accelerated Germany's defeat. This achievement, born of the meticulous work of propeller engineers rather than daring exploits of fighter pilots, deserves recognition as one of the decisive technological contributions to the Allied victory in Europe.